repair, restoration, rehabilitation, and retrofitting. Some of the pictures you can see in this. So the overview of my presentation is introduction to the topic, and then case list I'll share in two parts actually, so that I need not go through all 42 in one go. 20 and 22 parts I'll be presenting, and case studies of this case list I'll be presenting. That is a case, cause, analysis, and then restoration lessons finally. So this is my presentation overview. So basically repair, what do we do in repair? Actually, we all know the need for repair comes because when the cover is affected in the concrete due to climatic conditions or poor cover as per the specification, and a type of condition of the concrete, whether it is cracking, shrinkage, or creep, all the effects, we need to restore the concrete to original state in strength and for strength and durability. Then about steel reinforcement, we have various reasons. I'll be showing some of the case studies of detailing of the steel reinforcement event, the cases where it went wrong, and also the corrosion of the reinforcement and the fire accidents that can happen, after which we do the restoration and rehabilitation. Next is the geometry. Geometry is the dimensional tolerance of the structure, whether it is the sizes of the members, like thickness of slab, or sizes of the foundation, depth of foundation. All these issues will handle in the geometry, which also need repair to regain the original design dimension or design condition. Next is the restoration of the design parameters. All the design parameters, whether it is the percentage of steel, concrete strength, or concrete porosity, concrete durability parameters, all the design parameters, including the reinforcement concrete, we have to restore so that the structure will perform as per the design for its life, design life period actually. Next is the rehabilitation. The need for after repair and restoration, the structure gets rehabilitated for the serviceability of the structure. We all know the serviceability conditions of the structure, particularly the deformation and then the strength aspects of the structure. Finally, what is retrofitting? The retrofitting is the design intent change, the change in design intent. That means, for example, most of the cases it happened, we would have built the building designing for a ground plus 3 floors, and after some time, nowadays we all know about the TDR, transferable development right, due to which the developer wants to add 2 more floors. That is an afterthought. The designer has done the design correctly, but the developer wants to change the design base. So we have to retrofit the structure with that revised design intent. And similarly, design basis, change in design basis due to needs and code revision. That means needs are like we have designed the building for residential and later it is occupied for office or some other store or showroom kind of things where the loading conditions change, and we have to retrofit the structure for the revised loading condition. Next is the code revision. The code revisions we are seeing nowadays, whether it is IS 875, IS 1893, now IS 456 under revision for performance-based design. All these revision in codes, we have to retrofit the structure. And also we have seen about 40 years back, post-Kobe earthquake in Japan, all the structures in Japan, they have retrofitted for vertical acceleration of the earthquake. So like that, also now the climate change, which is we have been talking about, whether it is the temperature change or the rainfall intensity, flood levels, and earthquake revisions, all these, and rainfall patterns are changing. So for all that, we have to do the retrofitting for the structure. So retrofitting is more relevant. Good engineering will avoid repair, restoration, and rehabilitation, but even retrofitting is required to rehabilitate the structure for the revised design basis or design intent actually. So this is the overall topic encapsulation I have done here. Next is we should also be aware of forensic audit nowadays for any structure. As per National Building Code also, a normal structure also you need to re-evaluate every 5 years and assess its stability and durability of the structure for its design, residual service life design period. So forensic audit is the one in which we do the investigation and also find the adequacy of the structure and also compliance of the structure as per the original design intent. In case there are any deviations, there are any shortfalls in the forensic audit found, then we need to go for fixing the responsibility and also go for restoring the structure to its original design intent actually. Next, the responsibility of the engineers in investigation, in design, in planning, in construction, in engineering is very, very important. So we all have to understand our roles and responsibilities to avoid all this kind of need for repair, restoration, and rehabilitation. Next, very important thing is contractor all risk policy insurance to mitigate the risk. The risk is unavoidable some cases. So if in case any accident, any damage happens to the structure to restore, we need to have a contractor all risk policy for the builder and also professional indemnity insurance for consultants like us who design the structure, so that if there are any errors, human errors that have crept into the design, also the risk is covered. Ultimately, the developer should not lose. And lessons for future is finally a good engineering and good practice, good methodology of construction, and understanding the latest codal provisions at the beginning itself, and also if required, factoring for future requirements also is very essential. So now I'll start my part one in which the topics I cover are excavation, shrinkage, the defects due to formwork, staging. Staging also is very, very important. Many times we use double staging, triple staging for the high-rise roofs actually. And next is even the compound wall. Why I particularly mention compound wall here is most of the people think that a compound wall doesn't require engineering or design. But my guru also told me, who is a doctorate in structural engineering with gold medal, that compound wall is the most challenging design in engineering actually. Though it looks so simple, but it is most ignored, most neglected structure in the world, and maximum damages happen in compound wall. And wind, the failures are problems due to wind and pore water pressure. Underground pore water pressure is another cause of problems, and in fact, which require a repair and rehabilitation. Corrosion, of course, is the most common thing in steel, reinforcement and structural steel. And clay soils, expansive soils, or swelling pressure soils. So these are all the cases I'm covering in part one. So deep excavation. First, when we talk about excavation nowadays, most of the cities we have going below ground up to 5 floors or even 8 levels of parking, which require deep excavation and which require shoring. And if we don't do proper shoring, the problem starts there. So I'll share some of the cases. Excavation collapse during excavation, and then double staging collapse during concreting, canopy centering failures, and canopy is unbalanced shear And there are many canopy failures during concrete casting. So if it is not designed properly, the centering failures happen. And slab design failure due to torsion and corner span. We all know in two-way slabs, we have to have containing reinforcement in the corner to take care of the torsion, and it is mostly ignored in the detailing and the corner spans. Next is the flat slab design due to inappropriate use of direct design method. IS 456 has given the cautions for considering the direct design method. In spite of that, many times people miss this number of spans and difference in between adjacent spans, which call for repair and restoration kind of thing. And no final setting due to excessive retarder. In the concrete mix design, we use retarder nowadays in particularly ready-mix concrete. And the ready-mix concrete, we add retarder, and excess retarder will delay the setting, and too much of excess retarder will delay setting even beyond 36 hours, initial setting. And shrinkage cracks due to dry summer and improper curing. Also, many times we come across in most of the, and we restore that. And then foundation under design due to existing water stream underground. So this is one case where we had done the rehabilitation of the foundation using the micropiles, and insufficient design due to additional floors. That is, we have seen a failure in Chennai also, 11-story building, which was originally designed for 4-story. So like this, we will have case studies of all this poor water pressure due to closure of relief well, failure of slab due to closing down spouts, and water load due to one. It's a very classic case of missing small details actually. Collapse of compound wall due to expansive clays, failure of building and floorings due to expansive soils and improper drainage, and collapse of security wall due to unexpected flooding and improper reinforcement placement. So these are all the cases where we could have prevented these failures, but they happen. So it is better we do the proper design intent and design basis even before commencement of the planning and design. Failure of tower due to hailstorm and under thickness of tubes used. Failure of towers due to lack of anchors. This is very, very important. Most of the cases, tower stability depends on the resistance to uplift. And if we have a lack of anchors or adequate anchors, the towers fail. I'll be sharing some of the cases where towers have failed due to even the less than the design wind speeds, and bad concrete and uprooting, and excessive corrosion due to inadequate cover in severe exposure conditions. So these are all the cases which happen due to mismatch between design and construction intent and actual condition. That means we have a design intent. In design intent, we mention the grade of concrete, cover, exposure condition of the concrete, and reinforcement condition, and the construction methodology we mention. Suppose in the actual condition, if they don't follow whether the material properties or the construction methodology, then this kind of mishaps do happen. Next is the loading soil. Mostly geotechnical investigation is many times inadequate actually. So many people think that in one case in Bangalore only, where we have done even 20 bores of depth 20 meters, could not represent the soil condition properly. Though it was a rock, that's very, very important. Proper geotechnical investigation planning and preliminary investigation, and based on that we have to plan the detailed investigation to represent the complete soil profile. And then accidents is something which is beyond human control. So we have to also have risk mitigation strategy to account for this kind of accident that can happen, and material properties, construction methods, structural system, corrosion, expected life, and general loads like seismic loads, wind loads, dead loads, and live loads, inadequate consideration of the loading in the design, and in the soil settlements, liquefaction, expansive clays, and caving in during excavation. So these are all the specific cases I'm going to explain now in this part 1. And fire, blast, impact, and flooding, and materials, poor quality, wrong specification, shelf life, and structural system is always an engineering error. That means improper modeling of the structure. And then corrosion and life of structure, quality plan, quality assurance, quality control, quality audit, materials, works, and workmanship tolerance. So these are all the things which I'll be covering in my case studies now, which we are getting into the now takeoff mode. And so deep excavation, this is a very, very interesting case of mismatch between DBR and actual condition. Shoring, we all know if you have to do the excavation of 20 meters deep, so it requires proper investigation and proper shoring system to be considered, because this is a fast track project in which we have recommended use of active anchors, which you can see here in the deep excavation, because we expected that the soil condition after investigation, it has very highly varying soil strata, in which we found that there is a soft disintegrated rock below, which can be misconstrued when we do the shoring piles. It is very difficult to distinguish between soft disintegrated rock and hard rock. So we suggested not to go for shoring piles and go for active anchors. But because with active anchors, we are very sure about the performance of the anchors because we test every anchor by stressing the anchor. That's why we call them active anchors, not like passive nails that we use in deep excavation. So this is what we have done. But unfortunately, the execution contractor has taken exception, and then they have used shoring piles. But though in the same project where we had the uniform soil strata, the shoring piles worked, but where we had this soft disintegrated rock, we had the problem of this misinterpretation of the soft disintegrated rock as hard rock. And then this is the deep excavation before failure. These are all the piles, shoring piles with the cap. And this is the deep excavation where we had the uniform strata of the soil, where all the 20 meters deep excavation, it worked perfectly. Then this is the during progress of work, there is no problem at all. And so uniform soil strata, the shoring piles work perfectly. There is absolutely no problem. But when it comes to non-uniform soil, where we have this kind of, you can see the soft disintegrated rock, where the piles are supposed to be socketed to a depth of 2 meters, and the berm is supposed to be there as per the design about 1 meter, and then the sloping thing as per the design drawing. We can see that there is a mismatch between the actual design and construction methodology and what is implemented. So it is very difficult to control the soft disintegrated rock, maintaining the profile as per the design. This is a practical problem. But still, they have gone ahead against our DBR, and then there was a failure of this pile. You know, these wedge whalers highly depend on the these nails, and these nails depend on the wedge actually. And when there is a settlement in any pile due to inadequate bearing or inadequate socketing or inadequate lateral shear support to the socketed depth, then the pile will settle and the wedge will get released. Once wedge is released, the effect of this anchor is gone. So that's how this total piling has failed. So 5 months before, we have done the design check, and we have given the comments, geotech capacity, basis to be given, reference, and but we also have installed the structural health monitoring of the neighboring structures during this deep excavation. So we could actually assess the damage to the neighboring structures when the excavation failed actually. So it's very, very important. Professor Bharti Madam mentioned about the need for technology. So this was implemented in our project. And because of this vibration sensors, and we could exactly identify the time of the accident and also the effect on the neighboring structures. And we could recommend the rehabilitation of the existing structure to be utilized for occupancy. So these are all the very practical cases where this was a presentation made post-failure to the occupants of the building, and we could restart the activity by rehabilitating the deep excavation like this with the conventional sandbags, and we have put 20,000 trucks of soil actually within 48 hours. And then we put the sandbags and restored the stability of the existing structure. And then we have given the stability of the soil also. And then slowly we have rehabilitated the excavated line back with the normal nailing and gunneting technique. So this is how how we have cautioned the people, occupants of the building was there is an IS code where the vibration can be sensed by people, laymen. If you have the vibration felt below ankle, there is no need to think about it. People talk about vibration, but they don't sense how deep it is and how difficult it is. And then if the above ankle, inform your building manager, above knee, inform emergency rescue team. If above his, use emergency escape following inspection. So this is a very, very important codal provision to sense the level of vibrations. So this we have also verified the velocity of vibration, permissible velocity of the vibration is 12.5 millimeters per second. So average and peak pre-incident values we have recorded and found that it's not affected the existing building. So this is how you can escape from the building. The escape routes are given and public address system is there, and psychological factors, all that we have done. Next is the excavated soil dumped on the edge of the excavation line. This is mostly happening in most of the projects. So in the drawings, we specify also excess overburden. Already by doing excavation for foundation also, we are creating shear imbalance in the soil. And by dumping the excess excavated soil on the edge of the excavation line, we are increasing the overburden pressure and causing the failure. So this is very, very important point. So we have to have caution on disposal of the excavated area. Next is the piling test handling. So this is another, most of the cases we are having piling test failures and overturning in the rigs also, piling rigs also. Next is the double staging collapse during concreting. This is the concreting when people do because of lack of counter props in the slabs. This kind of collapse happen, and also lack of proper design and bracing for the centering also will cause this failure. And the canopy centering failure, as I mentioned, it is due to the imbalance in the shear, and the canopy failures will happen. And slab design failure due to torsion in the corner span. So 10-meter span base, 4 sides with the 20-meter by 20-meter courtyard. So we had the problem of corner slab cracking, and we had to restore that slab by using the shotcreting and gunneting with the structural steel also. Next is the flat slab design failure due to inappropriate use of direct design method. We all know that the span to span difference should not be more than 20%, and the minimum number of spans should be more than 3, and there should be proper plate analysis nowadays for this flat slab, without which these problems happen. And this is what we had to do the restoration by introducing the column capitals with steel after explaining. This is not the exact picture, but this is from the internet only. And so it is very, very essential to design the flat slabs. Be cautious when you are using the this direct design method. No final setting due to excessive retarder in the slab. So we found that in some of the projects, not many, 2 cases we found the excessive retarder has caused the lack of initial setting even after 24 hours.
24th name. Someday it's
Sorry, some administrative in the office. Yeah. So we investigated. Sorry. No final setting, and after we implemented timesheets and recorder edition to avoid this non setting of the concrete, initial setting of the concrete. Next is shrinkage cracks due to dry summer and improper curing. In dry climate, particularly places like Hyderabad, where the humidity is very low, so you will have the dry shrinkage cracks. So we have to have quick curing and introducing or controlling the evaporation by using the LDP sheets on top of the slab. And we normally, the risk of this shrinkage cracks is the pattern, the crack pattern that happens in the dry shrinkage will follow our yield line pattern actually. So we are always worried whenever we find this shrinkage crack, and we realize only after detailed investigation that these are only dry shrinkage cracks and not the structural cracks. So it's very, very important. So for that, we introduced the recording of the levels, 7-stage levels for the slab. Prior to pouring of the concrete, we record the levels of the form, and then post pouring of the concrete, we record the levels, and then before stripping, we record the level, and after stripping, we record the level. So with that levels recorded, in case post-tension slab, before stressing and after stressing, also we record. So 6 stages of levels are recorded. Next is the foundation under design due to existing water stream underground or estimated SBC. So this is the case where there was a water stream below the building line, which was not found during the geotechnical investigation. So SBC was estimated on higher side. By the time that was realized, the structure of the building is completed. And then we had to retrofit the foundation by introducing the micro piles. Next is the insufficient design due to additional floors. So this is another case where one of the building developed cracks in the columns just before occupancy, and it was referred to us. We found that the original design was done for the S+4, but the actual construction is cellar steel plus 6th floor. So there are 3 additional floors, and we had to introduce the box jacketing of the columns and concrete box jacketing, and then introduce infill walls to improve the floor stiffness for seismic resistance apart from dead load and live load. So this is another case. And another is poor water pressure due to closure of relief valve. This is another very classic case of climate change actually, particularly in Hyderabad. One of the projects we did in Hyderabad, we found that in the last 100 years, 1901 to 2000, there are 5 peak rainfalls about 100 years peak actually. And in the last 20 years, we found that there are 5 100-year peak rainfalls in 20 years only. So you can see the intensity of rainfall increasing, though the groundwater table is going down, the lakes are getting filled and flooded. So, which is causing this poor water pressure for the building. So, it's very essential for us to study this kind of cases also when we are designing the buildings, particularly with the basements and where the poor water pressure will have huge impact. It's a very interesting case. I'll explain in detail in the due course. So this is the podium structure. You can see the parking floor with the traditional column beam structure. And this is the cracks just due to poor water pressure. And we had to repair these columns, restore the structure, and rehabilitate the entire podium by giving relief to the poor water pressure. So this is what we have done in one of the projects. You can see the shear cracks due to the lifting of the podium structure due to poor water pressure. And here, this is what we have given the relief to the poor water pressure by providing the relief pipe. And maximum we allowed pour water pressure of 2 meters, and we could restore the entire podium back to the level by giving relief to the pour water pressure, and then started repairing the columns and beams, and also repaired the foundation. Next is the failure of slab due to closing of downspouts and water load due to 1 meter high parapet. This is a very classic case. And during the curing time, what they do is they close these downspouts and they forget before inauguration. And once the building got inaugurated and there was a huge rainfall, and because of that, there was a 1 meter water fill on the terrace. And normally we consider 1.5 kilonewton per square meter load, whereas 1 meter of water is 10 kilonewton per square meter. So then there was a large span slab with beams 18 meter span, and there was a failure in the structure due to this rainwater, and then the structure is restored by jacketing and also lifting the slab back and then strengthening the structure. Next is the collapse of compound wall due to expansive clays. This is a very common thing. People think why to provide 6 meter deep under-aimed pile for a 2 meter high compound wall. So this is the mental block most of the builders and engineers have, but it's very, very essential to design the piles even if it is required for the compound wall, if you want the compound wall to be safe. And some developers even argued with me, the cost of compound wall is very less, even if it collapses, I don't mind. But agreed, cost of compound wall is very less, but you will have parking beside the compound wall always. Nowadays, we have cars worth 1 crore, 2 crores kind of cars parked next to the compound wall, and cars getting damaged and claims going beyond 20 crores, though the cost of wall is 1 crore. So it's very, very essential to have proper design even for the compound wall. So this is the case we have done. Case study, you can see the parking next to the, actually this is a case also in Bengaluru actually. So we have done the study. We found that the wall is built without proper drainage system, and because of the dampness in the compound wall and also expansive clay, the wall has collapsed. So these are all the pictures of the collapsed wall, and we had to redesign and give the restoration for this compound wall which has collapsed. Hollow block walls are used, and engineering, proper engineering is not done. The drainage system is not considered. So that was the case of a compound wall. And flooring due to expansive soils. This is another interesting case. These are all ground plus one buildings, about 2,000 quarters for defense actually, for a defense project, in which it was entirely expansive clay. And every year they found that 5 to 6 buildings are failing. And this is the kind of damage that occurred to the building's walls. And the buildings are literally getting lifted and flooring is getting lifted. And they are dismantling these buildings because they find it is difficult to restore. But we have done the repair and rehabilitation by using out of box solution. Like instead of attacking the building, what we did is, because it's an expensive clay, we had to give the relief to the drainage so that the clay on which the building is resting is not subjected to the variations in the moisture. So that we have done. We studied the overall area and given a drainage solution to the clay. So after that, this further collapse and failures are prevented. So these are all some of the photographs of the failure in the masonry walls. And these are all the not settlement, actually it is the lifting of the walls. And you can see, you can clearly understand the lifting of the building, actually, arch action in the building. So these are all the photographs of the settlement. Next, collapse of security wall. There is a difference between compound wall and security wall. Compound wall is a normal boundary wall with the 2.1 meter height, and it's just protect the boundary. Whereas security wall is something which is real security in defense and all airports. We use this. Height of wall is 3 meters, and it will have the concertina coil above that, and then barbed wire above the compound wall. So overall height will be about 12 feet or 4 meters even, including all these security systems. And we have this solar fencing also on top of this in some cases. So this is the aerial view of that site where we had this boundary security wall here. And you can see the occupancy encroachments near the airport even. And then there was, they could not build a compound wall here, a security wall here, due to this encroachment. And before inauguration of this project, what happened was, due to excess rainfall, there was a flooding, and this, you can see the downside here, lake. And so this portion of the security wall has collapsed. So what I'm trying to say is, even while we design the security wall kind of things, we have to study the overall topographic features and overall risk, and design the things. In addition to the actual flooding itself, there was a construction problem also that we could find only after investigation. You can see this is a concrete wall. The whole wall has overturned and due to the excess water pressure. And then we thought that it is a natural failure due to the flood. But when we did the detailed investigation below the wall, we found that the reinforcement given in the drawing versus the reinforcement provided actually is a lot of difference. So that was finally decided to be the cause of the failure. And so the detailing and the implementation of the bar bending schedule and the provision of the reinforcement, this is the failure of the wall. You can see failed wall. So this is the clear picture of the collapse on the corner. And so this is the flooding that was happening because there is no wall on the encroached side. We built the wall. So we did a detailed study and analyzed the cause of the failure. Now I'll present you some of the cases of failure due to wind and which will cause, so failure of tower due to hailstorm. This is a very good, interesting study where normally we design for the wind, we don't design for the hailstorm. As per the code, where we take 0.6 Vz square as the wind pressure. But the hailstorm causes much higher pressure actually. We found that the tower, though it was all safe, but it has failed due to the hailstorm, and direction of the hailstorm, direction of the failure we found, and we felt that it is a rare case of failure. So we have to keep in mind this kind of things also. But in addition, we also found that the thickness of the tube that was used is below the design thickness. So that was also one of the causes of the failure. And next is lack of anchors, failure of towers due to undergrade bolts. This is even very interesting. The bolts that we specify for joints or 5.6 grade, which will give you shear capacity of 3160 and bearing capacity of 7320 kg per cm square, whereas 4.6 grade will give you 20 to 20 shear and 4440 bearing. So we found that when the failure happened, when we went for investigation, they have cleaned the entire site. But I thought that, as people say in forensic, every criminal will leave some trail behind. So when I verified the site, I could find one bolt, and I could find that that bolt is 4.6 grade, and bolt has got sheared. So I could fix the cause of failure with one bolt. So that's why it's very important to understand the need of right grade of the bolts in joints, in structure. And due to missing bolts is another thing, and failure of tower due to bad concrete and uprooting. So these are all the cases. Here you can see anchorage. The whole foundation got toppled with the wind, which was much less than the design wind speed. And when we investigated, we found that the anchorage was not adequate. And so these are all the actual anchorage failures of the rooftop towers. Here you can see the bolts are even left in the foundation itself, and tower has come out. So multiple failures we have studied. And here, this is another classic case of net area that we have in the code, that is A plus B, net area of the section. Normally, you have to have the staggered bolts, working lines. So here you can see, so with staggered, we take 2 bolts area deducted from the entire gross area. But in this case, the fabricator has put 4 bolts in the same cross section, and because of the inadequate net area from the design, the angle has failed in tension here. So this is a very, very interesting case of failure of tension. And here check nuts. Normally in the detailed drawings, we provide actual nut and check nut. Second nut we provide to avoid the risk of failure and redundancy, to provide redundancy against the failure. But here you can see there are no check nuts, and the whole tower overturned due to lack of check nuts. So this is another inadequate anchor for foundations. So there are multiple. We have investigated at least 50 to 100 cases of these tower failures across the country, and we found various reasons, and these are all the photographs. Very interesting cases. So this is the failure of the towers. I'm not explaining because we have very more interesting cases, but wind failure, this is an interesting case study. That's why I'm showing all the different check nuts and lack of knurling, we call. There should be minimum 3 threads above the check nut. And here you can see there are 3 threads, and here it's not there. So, and here also you can see there are no 3 threads beyond the nut. So it's very, very important final checking in the final acceptance test, and missing bolts you can see here. So these are all the tower cases, some of the failures that happened, and these are all very important towers, communication towers, you know, for security and all, and such towers failed also in important times. These are all the tower failures. Not excess wind actually, even so. That's here you can see that again tension failure due to bolts in the same line. Next is the corrosion, excessive corrosion due to inadequate cover in severe exposure condition. So IS 456 has given clear direct guidelines for following the cover for normal, mild, and severe extreme exposure condition. If you don't follow, this is what is going to happen. This is a steel structure. You can see it's a chemical factory where the fumes are very highly severe exposure condition, but they have not taken the care in the design or probably execution, providing the adequate cover and adequate protective coating for the steel structure. And this is the condition of the steel structure after even 5 years of occupancy of this building. And so this is to be restored. Actually, we visited to restore, but we found that the damage is beyond the control, and we had to recommend the demolition of this building. This is another reinforced concrete building. You can see the inadequate cover causing the exposure, severe corrosion in the reinforcement in slabs, beams, and columns also. And so this is what happens if you don't provide the adequate cover to the reinforcement. And this is the corrosion. You can see the stirrups, you can see the main bar, even without opening the concrete. So you don't need what you call rebar locator to identify the rebars. So corrosion. And here also column, you can see the ties and the main bars in the column also. So this is end of part 1. And if you have any questions up to here, if you are happy about the way it is flowing, it's fine. Otherwise, I'll try to modify my presentation in part 2. Any questions? You can open.
Mr. Surya Prakash.
Yes, sir.
There are 3 questions given by our M.Tech students.
Okay.
I read them before you move to the next part.
Okay.
Question number 1. When we say deep excavation, you mentioned deep excavation. You know, this question is related to that. When we say deep excavation, is it a relative parameter, or beyond what depth we call the excavation deep?
Yeah, that's a good question. Any excavation beyond 3 meters, we call it as a deep excavation, which requires shoring and strutting, actually.
And the next one is, you mentioned a case study of shrinkage cracks developing, which were same in pattern to the yield line.
Yeah.
And the structure was still in the beginning of its life. Did yield lines develop so early in its life, even when it was not yet loaded with the service loads?
Yeah, that's what we observed. In fact, the shuttering was in place, but we know that within 24 hours, structure starts getting to its stress patterns, actually, within 24 hours itself, while setting, after final setting. So this is what we observed, the shrinkage. So the shrinkage also happens in the stress flow pattern, actually. This is our observation. I don't have any research to support my claim, but I observed this in at least 4 or 5 projects, where particularly flat slabs and normal 2S slab, we found every time we get an alarming call from the client, we go inspect and find that the cracks are only shrinkage cracks, because we verify the depth of the crack and all. And they exactly come in diagonal direction from the column. And but we check the levels, everything, and we found that the levels are also perfect. There is no deflection really in the slab, because without deflection you cannot have a crack in yield line pattern also. But we found that these shrinkage cracks have followed the pattern of yield line. It's an interesting observation.
And the third question, you mentioned about the problem of the excessive retarders used in the RMC.
Correct.
How was that problem solved?
Actually, yeah, it's not the problem with the designer or the supervising engineer. Normally, what they do is they will give a tin of retarder to the truck driver, transit mixer driver. So what they are non-technical, actually, and they try to dump the entire retarder in one go, so that they don't have to worry. They think, actually. So once it happened in one project, about 36 cubic meters of concrete did not set. When we investigated, we found that the amount of retarder given was correct, but you have to give the dosage of retarder every hour actually, one dose every hour. So at the plant, they have given the dosage required for 3 hours, anticipating some delay in the transit, and the driver has poured like we suppose we are given antibiotic for 3 days. You take antibiotics three days dosage in one go, thinking that your fever will go fast. But same way, the driver would have thought, layman thinking, the retarder he has poured and concrete never set. So
yes, yes, sir. There is one more. Yes, sir. There is one more question by Dr. Bharti Ganesh. Yeah, he will ask.
Sir, while mentioning about the security wall, you mentioned that the lakes were filled and the surrounding water table receded fast. This is the observation common throughout. I am from a Malnad area. Earlier, during my childhood, when there was rainfall or flood at least once in 3-4 years in the nearby river, all water table used to be we used to get rise, and then at least for 3 to 4 months there used to be all the wells used to be full. Now the scenario is totally different. Not just in our native place, everywhere surface runoff has percolation has reduced a lot, which results in surface runoff and flash flood.
Correct.
So what is the reason for, is it the reason for such flash flood is blocking of pores in the soil, or how it is to be addressed? Because finally water table has to be increased, but that's not happening, and water is flowing and creating a flash flood.
Yeah, this is a very big problem that entire humanity will be facing with urbanization actually. We have runoff coefficients, for rural areas, agricultural land, and urban areas. And urban areas, your runoff will be much higher because the absorption coefficient is very less. And we are covering entire area with concrete or pavements or anything, buildings and all that due to human occupancy. So because of that, the absorption reduces and runoff coefficient will be high, and so there will be quick runoff. So normally we would have designed the sewers and all considering original about 50 years back, 30 years back runoff coefficient, but now they are no more valid, and we have to retrofit even the sewer systems to considering the present runoff coefficient. That's what exactly happened in one of our projects.
Thank you.
Yeah, Shri Surya Prakash, before you move forward, there are some compliments also in the chat box, and Dr. Perumal has mentioned excellent material and beautiful presentation. And there are some participants like Ms. Ashwin who want to know whether your PPT can be shared with them.
Yeah.
And
maybe, though I have not mentioned my client names and all, it should not be, I mean, it's a confidential information I am sharing for technical presentation. So if anybody needs, they can approach me personally, depending on their background and all. It is for research education purpose, I can share, not a problem.
Yes. And I request the participants to feel free to throw in the chat box or QA box. Yeah, Shri Surya Prakash, please go ahead with your part 2.
Thank you. Thank you. So part 2 is a structural system, which is very, very interesting for all structural engineering. Earthquake, construction methods, temperature, reinforced earth walls, and masonry walls. This is very, very, I always mention, everybody thinks masonry wall is job of a mason. But actually masonry wall also requires engineering in design, stability, and construction. So this is what many people are missing. So I'll share the cases of failures of masonry walls. And most of the buildings you see cracks in the masonry walls, that is due to improper planning, design, and construction also. Next is the water pressure, and then material handling systems, and then masonry fire and blast. So these are all the cases I will be presenting in part 2. Please don't mind, I will go a little faster to cover my time. I have to finish in 45 minutes, all these cases. Failure of silo due to wrong friction coefficient. Very interesting. Earthquake resistant design, fire rating of steel structures, inverted beam and neutral axis above the slab without double layer reinforcement, and lack of weatherproofing and top temperature reinforcement leading to cracking in upper floors. This we see, I don't know how many of you would have observed, even in a steel plus 5-storied building, the 5th floor invariably will have cracks in the walls, more than 4th floor and 3rd floor. That is due to the free expansion of the terrace slab, which we can only contain by either doing weatherproofing or providing a top layer reinforcement. Those structures are not required for the sake of temperature. We have to provide the top layer reinforcement. And then removing counter props without pore strip being done. This is another interesting case happened in one of the projects. I'll share that. Crushing in anchorage zone due to honeycombing in bursting reinforcement. In post-tension slabs, it happens in many cases where we have a lot of reinforcement congestion near the bursting zone. We provide the bursting reinforcement, and when we do the stressing, the concrete, because it will have a lot of honeycombs due to reinforcement congestion, so there will be failure of concrete. And when we restore them, of course, I'll share how to restore that. And precast wall panel segregation in concrete. This is also an interesting case. Failure in bottom slab of W section due to prop settlements in sandy soil. Excavation site failure due to lack of shoring. And shoring pile failure in clay soils due to saturation and water pressure. Lifting of flooring due to poor water pressure. Wall collapse due to no design and support. And structural under design and construction mismatch. So buckling of bracings due to erroneous effective length, or in steel structures it happens, improper consideration of the effective length. Reinforced earth wall failure due to missing corner joint and in trumpet interchange. And pile load test failure due to integrity of pile integrity is very, very important, and mostly it happens in piles because of the small diameter and deep pile, 40 meters and 30 meters kind of depths, and concrete being not properly designed for flow mix or the proper method of concreting. And corrosion in plinth zone due to inadequate plinth height, seepage in flexible pavements due to natural ground level and subsoil water, salt by cut-off trench and VG bitumen tack coat, and crane failure due to structural system unsymmetrical supporting and detailing, all very interesting structurally, and tower failure during stringing condition due to doubling of the wind speed span as conductor left on rollers unusual. So this is a very silo, very innovatively done. You can see the what you call corrugated sheet, GS sheet used as a skin for the silo. But unfortunately, the designer, I don't know whether it is a later change by the execution contractor. The designer has considered the friction coefficient for the grain. This is a grain silo, a normal friction coefficient, and you know, due to the horizontal corrugation, this is very good for hoop tension, this system. But when it comes to the loading, we found that the friction coefficient is much higher because of the corrugation and the higher load, and it caused the failure in the silo has tilted towards one side due to the higher friction coefficient. Next is the structural system model behavior detailing. This is a very, very common thing happening nowadays. People are analyzing the structure using any software, but they are failing to study the bending moment, shear force diagrams and identify the primary beam, secondary beam, tertiary beam kind of thing. And I was referred this building thinking that people thought that it was a waterproofing failure. And there were cracks, profuse cracks in the slab. When I studied in detail, this is the below the slab actually. I could sense that there are grid of beams and there is a probable detailing problem. And this is the beams. You can see very difficult to identify which is primary, which is secondary. Unless you study the bending moment diagrams, you will not know where the maximum shear is and which is the primary beam, secondary beam and all. And you can see the cracks in the beams also. And we found that it requires treatment by all means and correction of the reinforcement also. So we have recommended the rehabilitation of this or by restoring the reinforcement as per the design requirement, because the design was faulty, detailing was faulty in that structure. So we had to give the complete slab. Slab reinforcement was okay, but we had to repair the concrete, cracked concrete. And we have to restore the bond stress between the reinforcement and the concrete. And so beams we had to do with additional reinforcement which is required. And then walls, we had to do the stitching. The masonry walls also cracked due to the excessive deflection in the beam. That is beyond the serviceability limits in the beams, and they are stitched. So this is the photographs of some of the beams and all before repairing, and they are repaired and restored, and as per the details given by repair and restoration system. And we did the grouting, we did the stitching, we did the reinforcement jacketing, and all the methods of repair, restoration and rehabilitation. This is another interesting case, rebar detailing of the grid beams, so this is a failure in the beam at the joint in the grid beam. The reason for this is the primary beam reinforcement is curtailed, assuming that every joint is a grid. Though in the structural drawing it is clearly given column to column, you have to continue the reinforcement. The engineer on site interpreted that joint as a support instead of column as a support, and he curtailed all the main reinforcement. Because of that, there is a huge shortage of tension reinforcement in the span, and this had to be repaired. And this is the site notes that the engineer has done. Levels are recorded. There was excessive deflection, and so we had to give the entire stitching of the joints using the structural plates and shear connectors. And this was repaired, restored, and rehabilitated the structure. Next is case study of earthquake, Gujarat earthquake, where I had the first-hand experience. Post-earthquake, probably I am one of the few handful of engineers who are in Gujarat after the earthquake. And I spent a week's time there studying in detail the failures of the building, because this is the first urban earthquake in India, causing huge damage to the urban structures. So you can see a lot of flaws in the detailing and design we observed, and people started doing cosmetic treatment to the failures. So repair, rehabilitation, restoration, we have to see that the work commences only after valid certification. We should not allow any non-technical people to commence this restoration work. So here you can see the shear zone. As per 13920, you have the minimum tie requirement right below the beam for a zone of shear zone of at least 800 mm, 1 meter. It should be there, but hardly there was any containment reinforcement, and even the tension, the main reinforcement was less, and concrete got crushed because of that. So here there are so many columns and shear walls failed due to inadequate detailing. So we found that there is no geotechnical engineer report, there is no structural engineer report, there is no construction engineer report, and there are no proof consultants in any of the projects. We could not find any data. And interestingly, there was a fire accident in municipal office after that earthquake because they wanted to destroy all the documents. So this is the observation, this is the actual report we submitted to the government because I was part of the expert committee member along with Professor A.S. Arya, as mentioned in my introduction. So this is the earthquake, post-earthquake study that has given me opportunity to study all the causes of failure. And we have even given the generic solution for, because there was lack of engineers in that area. We can't expect every building to be analyzed in detail, and we had given the recommendations for generic solutions to reduce the stiffness difference between, like soft story concept, the stiffness difference between the open state and the immediate floor, you can reduce by introducing a tie beam at the foundation level or plinth level and building the infill masonry wall to avoid any future failure. And calculate the number of walls above the stilt and match the thickness by introducing less number of walls but higher thickness walls. So this is what the solution we have given quickly, and it was implemented. And next case study is the fire. Here what you can see, this is a post-tension slab, a 13-meter span, and there was a fire overnight, and you can see the entire tension reinforcement got exposed. But surprisingly, the deformation in the slab is within the limits. There was no excessive deformation or recognizable deformation. Even the drop panels, you can see the reinforcement got exposed. And fortunately, this is the top of the slab where we have taken the levels. And there were though cracks, but they are not caused by the fire. There were earlier cracks in the due to shrinkage or joints actually. So we could restore this slab by just doing the shotcrete and reinforcement jacking. Next case is the structural steel warehouse failure due to the fire, due to inadequate fire rating for the steel. And steel failure, you can see the I-beams getting twisted even. This is the I-beam getting twisted due to the fire actually. So steel loses its complete strength capability in higher temperature. Next is the blast. This is a masonry wall, 14-inch masonry wall residential building. Just due to gas cylinder blast, this whole wall got blown off. Of course, unfortunately, family died in this accident. But we have to think when we are doing the building. So after this, I never allowed any gas cylinder to be kept within the kitchen. It's always better to keep the gas cylinder outside the kitchen and have a pipe inside. So that is the solution, because designing the structure for the blast will not save the people actually. So you have to avoid the blast within the building. So next is the inverted beam and neutral axis. Most of the people I have come across, when the architect or user wants clear height, we simply say, okay, do the beam inverted. But we fail to check that the neutral axis, when you change the beam, sometimes the entire slab will be in the tension zone, actually, in the span, in the large spans, actually. Because we keep the beams at very close space, so the slab thickness will be 100 mm or 115 mm, 125, so less. Because of that, we found that there is a through crack due to tension in the entire slab, and the designer or detailer did not provide the double layer reinforcement, and because of that, crack propagation starts from the top. Because in the top we don't provide the reinforcement in the span, the slab started cracking and failing. So it's a very interesting lesson of inverted beam. Whenever we use inverted beam, better to check the neutral axis and provide Neutral axis is even within the cover zone of the next slab. You have to provide the tension reinforcement double mat in the slab. Next is the lack of weatherproofing and top reinforcement. So this is the cracks you observe normally in the top floor, even in steel plus 5 floor, and thermal expansion in the top floor. If you have weatherproofing, you can contain the thermal difference, temperature difference, or at least if you provide the temperature reinforcement in the top layer, you can avoid this cracking in the top floor. So this is a very frequently observed. That's why I mentioned this in my study. Next is the removing counter props. This is another interesting case study of a post-tension slabs. In fact, this was a 14-story building in which in our design brief, we clearly mentioned if you have a pore strip planned here and if you have pore strip not closed here, you must have 2-level counter props. Normally code says you provide 1 counter prop, but because this is a pore strip, the slab is not yet attained its original strength. So we always suggested 2-level counter props, and you should not have pore strips in more than 2 levels, unclosed. So this is a very interesting case study. What happened was during the night concreting of the casting level, because of the need for props, they have removed the counter prop thinking that this is not required. And for engineers, it is very difficult to identify the fitters removing the counter prop at that level actually. So it so happened because this is a pore strip, the slab span has become 7-meter cantilever, and then the slab cracked in the top here. So this is the actual photograph of the PT slab before pore strip is concreted, and so this is the pore strip in the drawing. These are the cracks, and we have done jacking up of the slab, and then pore strip is closed, and we have repaired this concrete by grouting, and also where our reinforcement is found that it is inadequate, we added the reinforcement and jacket. So this is the hydraulic jack, mechanical jack used to lift the slab to original. Otherwise, the slab deflection was about 10 inches means 250 mm deflection was there. And we have jacked up to acceptable limit of the deflection. Next is the crushing of in anchorage zone due to honeycombing in bursting reinforcement details. So crushing of concrete during stressing in anchor zone, tendon yielding during stressing, this is another case of failure, and cutting of tendon during grouting. So after grouting. So these are all the things we have done in PT slabs restoration. This is a very critical case of precast wall panel segregation in concrete below rebar, unstable due to additional water being added in transit mixer. This is another classic case of driver adding water, which was requested by a mason actually. So this is the photograph of the wall panel. So you can see the reinforcement pattern in the wall panel, and this is the excess porosity that happened in the concrete due to the excess water cement ratio. And segregation, micro segregation I call it, because when you have excess water, we learned in our concrete technology that due to excess water cement ratio, there will be segregation in the concrete. So what happened is, when I went to a site, I found this, when they're curing, I found the reinforcement pattern in the dampness. I asked my engineer, he said it is a common thing happening in every wall panel. Then I said it's uncommon. So when we investigated, we found that there is an excess water coming out when you are doing the compaction. So then I started verifying design mix was okay, water cement ratio was very less, below 0.4. But the actual site, when we checked, we found excess water. We checked, then we found that the driver finally agreed that mason asked for excess water, and he did that. Next is this is a W aqueduct which we designed. of course, quite long back. We took the advantage of the W section, and the neutral axis is falling above the slab as usual. It is like inverted beam. But this is a 5-meter cantilever, 10 meters span, and another 5-meter double cantilever. And this was on the seashore. And due to the rainfall, due to sandy soil, there were settlements in the props. In one of the casting of the this segment, there are 60 segments of 20 meters like this. And when the settlement, the prop settled, they did the concreting of the base slab only, and wall was not done. And there was a crack in the slab. And there was a huge debate what to do, should we dismantle this whole thing. Then I said that once we cast the slab, this cantilever portion concrete in the base slab will get into the compression, and this crack will get closed. So we did that, and after casting of the wall, we jacked it up, and we did the casting of the wall. And after deshuttering, we found that there is not even a water leakage, leave alone the crack. So it has become watertight due to the compression. Next is the excavation site failure due to lack of shoring. So this is the thing that I have shown in the beginning also, excavated after. Next is we have this, when we do the excavation, this is what active anchor we call. Effect of pre-stressing is that we are balancing the unbalanced shear in the soil due to the excavation. And this stressed zone will form the pre-stressed compressed soil, which will form which will compensate the lack of shear support from the removed soil actually. So this is the concept of active anchors. So, and this is the shoring pile failure. This is another shoring pile actually. So there was one photograph I'll show you. So these are the shoring piles analyzed in Plaxis, and found that here you can see the separation with the soil after casting of the piles and after casting of the thing. So we had to restore this. That means there was a bow shaped failure in the piles and the capping beam. So this we had to analyze and restore the stability of the side slope actually. Next, lifting of flooring due to poor water pressure and lack of relief valve. So this is what initially also I explained. This is the podium slab. There was a swimming pool on top of the podium slab, and we found that this podium slab got lifted. And so this is the 2 floors got lifted due to the poor water pressure. Of course, this is a magnified one. And this is the jacketing we did for the columns with the shear connectors. And this is the water pressure permeability diagram that we have done. And we found that there is an excessive poor water pressure by the pattern, and there was a lake. Next, wall design collapse due to design and support structure under design and construction mismatch. So this is another block wall masonry with the large windows actually. And there was a collapse of these walls due to wind speed not even exceeding 50 meters per second. So there was a problem with both design and detailing of the wall and also the structure. So we had to give the strengthening for the structure by introducing the bracings, and also we had to introduce the moment connections in the large window panel and restore this structure. And then, so this is the analysis, and these are the bracings that we introduced. And then we had introduced the cross bracings at the joints to reduce the deformations and to save the walls. So this is the actual plan bracings also introduced in the floor plan. So overall deflection was to be controlled, and then masonry we had to detail by introducing the bands and mullions in the masonry as per the stability check that we have done for the masonry. Next is the buckling of bracings due to erroneous effective length. So here in this tower, the failure of this bracing was found due to inadequate effective length considered in the design for this bracing. Next, reinforced depth retaining wall. So this is the trumpet interchange and this is the RE wall with the anchors, nails, anchor, soil anchor. And this is the corner which looks like a column, but actually these are only blocks, non-structural, just blockage of the corner. So they had two sides wall panels, but not connected structurally integrally. So this has caused the failure of this wall, and there were many cracks in the RE wall. And this is happening in many cases. After we did this work, we came to know that most of the RE walls are failing due to inadequate detailing and inadequate nailing. So these are all the things, and we had to restore this by doing the anchorage again and restore this work. So we anchored to the retained backfill back, and all the panels are tested after the restoration of this, and in the Plaxis this was analyzed and found it is safe. Next, pile load test failure due to integrity of pile. Failure of initial pile load test due to improper augering. This is another thing. Many cases, theoretical pile capacity and initial load test, there is huge difference. There was 60% of the values only we could achieve. And we found that this is due to the improper augering technique. So method of augering determines the skin friction. So mechanical augering or manual augering we have to consider in the beginning only and ensure that the same method is followed before the initial pile load test. Next is the corrosion in the plinth. You can see the corrosion happens in the towers in the plinth level due to water level, waterlogging, and this was also solved restored by increasing the plinth level from 300 mm to 500 mm. We embedded the steel in concrete. Next is the seepage in flexible pavement due to natural ground level. So this is the runway actually, aircraft runway. You can see there was water seepage formed in patches, and when we investigated, we found that there is because of the hilly terrain, there is a water table level above the pavement, and then we have created the drainage around the runway, and we also done the tack coating with the VG bitumen, and then the problem of seepage is solved. Next, crane failure due to structural system unsymmetrical support and detailing. So here, actually this question I ask every engineer, structural engineer, about the portal frames, symmetry, unsymmetry. Not now, even before 30, 40 years I've been asking this question, because it's a very important 5 parameters to determine whether a particular structure is sway or non-sway. The boundary condition, the geometry, the material, the sectional property, the loading. So as a structural engineer, we have to have this understanding of the symmetry in the structure. When this problem is brought to me, they are trying, this is a portal crane moving on wheels. And when they approached me, I found that there is an asymmetry in the support condition, and we have restored the structure to the symmetrical condition, and then it started working. Finally, this is another case study of construction stage. This is the transmission towers. We have rollers to pull the cables, and as per the design windspan, we always consider null point to null point. That is one span, 300 meters. But we found that in that particular case where there was a failure of the tower, series of 7 towers failed, because of the rollers, the wingspan got increased from 300 meters to 7 times, 2.1 kilometer, or at least to 600 meter, and the failure happened. So construction condition also there was a difference. Normally we are not supposed to leave the conductor on rollers because to maintain the wingspan. And if you want to continue the same methodology in the design, we have to consider the larger wingspan, which is not economical. So you have to lock the conductor on rollers before leaving the site. So this is a lesson learned, and this is a tower we could not restore. The towers have failed, and this is the case. So finally, the structures, prevention is better than cure. So we have to train engineers, motivate engineers to be engineers, and enlighten stakeholders to engage engineers. And nurtured engineering gets better engineers. Obviously, if we use engineering only, we get better engineers. Buildings get distressed without building engineers. So no causes or remedies for projects with good engineers. So this is my conclusion. And repair, restoration, rehabilitation, and retrofitting we can do, and with engaging good engineers. So thank you very much. And some of my lectures are available on my YouTube channel also. You can connect to my YouTube channel, Pannada Surya Prakash, or contact me on my email or mobile number. So thank you very much. Now we can take any questions.
Thank you, Shri Surya Prakash. Now I request the participants once again, in case you have questions, please post them in the chat box or Q&A box. And meanwhile, I have collected here some questions. I move ahead with them.
Yes, sir.
Yeah, just 1 minute. Yeah. Yes, I have about 3 questions here with me. Question number 1. You mentioned a case study of curtailment of reinforcement at the junction of primary and secondary because of the wrong understanding and interpretation of drawings by the site engineer. How was the additional reinforcement provided at the junction?
No, even the additional reinforcement was not there. They have curtailed thinking that junction is a support.
The question is, how was it restored? Like, how did you give the additional reinforcement?
Yeah, we have used the steel plates, and we have given in both the directions steel plates, and given the shear connectors through the shear plate, and we have restored it.
Yeah. The next question is, do we have codal restrictions for using inverted beams?
No, there is no code restriction. Before I do this, I just want, we did even the load test after the restoration, and we found that the actual deflection was much lesser than the design calculated deflection. So the strengthening worked perfectly well. And yeah, coming to the inverted beam, there is no codal provision as such. It is for the structural engineer to understand the behavior and identify the neutral axis and provide the required reinforcement. Otherwise, code provisions give clearly that in any tension zone, any calculated stress you have to have the reinforcement. So if you don't have the reinforcement in the calculated tensile stress zone, there will be cracking. That's what exactly happened.
And the last question I have with me right now is, you mentioned the case of 2 floors getting lifted due to poor water pressure. Was this problem solved, and if how?
Yeah, we have solved that problem as I have shown in my pictures. We have given the relief to the poor water pressure, and then we have allowed the structure to come back to its original position, if not 100%, at least to the 80% level, acceptable deformation level. And then we have repaired and restored the structural element, and the structure was completely rehabilitated. And already this is more than 5 years old, or even 8 years old, I think. And there is no problem after that, even with excessive rainfall.
I request my colleagues to let me know whether there are any more questions. Please check chat box. Otherwise, we move ahead.
Sir.
Just 1 minute, sir.
Sir, I have one question. Can you hear me, sir?
Yeah, I'm able to.
During the stability check of structures,
Yeah.
this check is limited only to extraction of core and assuring the stability through strength of concrete. Can you please comment on this, sir? As per the government norms, all structures at regular intervals have to undergo stability checks.
Correct.
This is through extraction
Normally,
of cores. Can you
normally
please?
if we have the drawings available as per the detail, we verify the structural stability theoretically, and also ensure that the concrete strength which was certified during construction is also verified by doing core test or even UPV test, depending on the importance of the structure. We ensure that the reinforcement condition also is verified by profometer or rebar locator, with which we can identify the level of corrosion in the reinforcement. So we have to ensure that the reinforcement quantity is available, quality is intact, and concrete strength is available and condition is intact. After ensuring these two parameters of concrete and steel, we also verify theoretically the adequacy of the available reinforcement and the concrete strength. And then we verify physically the entire condition of the structure with the cracks or no cracks. And also we even verify the cracks in the partitions, false ceiling, flooring, everything, to ensure the serviceability of the structure or dampness due to plumbing line. And in many cases, people miss this in particularly high-rise building. The plumbing lines should be given adequate provision for the permissible deflection in the structure, permissible sway in the structure. So we consider all that and then certify finally the stability for another 5 years. No structural engineer can certify the stability for the service life of the structure unless it is periodically tested and certified.
Thank you, sir. Gautam, any more questions are there? Okay, thank you. Over to Dr. Raghav, sir.
Yes, sir, and there are some compliments also in the chat box, and I thank the participants for those compliments. And also, I request the participants to provide your feedback with the feedback link which is given in the chat box. And in the end, I request again all the participants to help us coming online with their videos for the snap. And with that, I will be coming to the end of this session. Yeah. Shri Engineer Surya Prakash, our sincere thanks for sharing your value experience and knowledge with us. We were flooded with so many case studies. I think, as I remember, 41 was the last. This highlights the importance of this subject of 4 Rs. As I had told in the beginning of the inaugural session today, you have always supported us by agreeing readily to share your knowledge and experience with fellow engineers and students. This quality of yours, thank you, sir. My sincere thanks to all the participants. And I also see a few names of the resource person of this FDP and a few other names of known colleagues and friends in the students list. My sincere thanks to every one of them, but I should mention here eminent persons attending program, a few Dr. R. Jagdish, Chief Operating Engineer, Consultants Consortium, Bengaluru, and former President ICI and former Professor, Department of Civil Engineering, University Vishnu College of Engineering. And I also see Dr. H. Shardabai, retired Professor, Department of Civil Engineering, University College of Engineering, Bengaluru. And also one of the resource persons, Chandramouli SV, consultant, structural art section, SCM consultancy and engineering the services, Bengaluru. And Professor Krishnamurthy also is there. And I am sorry if I am missing any other news. My sincere thanks to all of you for being online, and thanks everyone. And with this, we are coming to the close of our first day session. I request every one of you to have your cameras on so that we can take a snapshot of this session. At the end of every session, we will have a snapshot. Yeah. Thank you, Engineer Surya Prakash.
Yeah, thank you, sir.
Yeah, and once again, participants, please fill up the feedback form. And very quick, all the videos, please on. 55 participants, please come online. And of course, one is class with about 30 students. Yeah. I request the organizers to take the snapshot soon and let me know when it is over.
Good evening, ma'am. Good evening, sir. So happy to see you, ma'am.
There is a message, camera is disabled. Please enable all the cameras. Yeah, all the cameras are enabled now.
Surya Prakash, sir, all our PG students are participating. This subject is a part of their curriculum. Actually, we offer restoration rehabilitation subject in 3rd semester, which is fast track. Thank you.
Yeah, okay. With that, thanks everyone. And we have taken the snapshots. Yeah, and we are coming to the day one. Thank you, sir. Thank you for joining.
Thank you, sir.
Yeah, and we will be meeting. Yeah, please. We will be meeting tomorrow afternoon.